Section 4.2 is titled Applied Congruence and Triangles. Applied congruence and triangles. So we've talked a lot about congruence, congruent segments, congruent angles. We also in 4.1 started talking through triangles. Today we're going to combine what we know about congruence with triangles. So two figures in general, any two figures are congruent if and only if all parts of one figure are congruent to the corresponding parts of the other figure. Two figures are congruent if and only if all parts of one figure are congruent to the corresponding parts of the other figure. So here we have two triangles. Notice the measure of angle A and the measure of angle F are the same. The measure of angle B and the measure of angle E are the same. The measure of angle C and the measure of angle D are the same. All the angles correspond to congruent parts of the other triangle, and also the segments are congruent as well. Segment AB is congruent to segment FE. BC is congruent to ED. Segment AC is congruent to FD. So we have all the sides of each are congruent, all the angles of each are congruent. So we can say that triangle ABC is congruent to triangle, and we name it in the same order. So A matches up with F. Notice those are the two that had the same angle measure. So F, whoops, that's not an F. ED. E is the one that corresponds with B, and D is the one that corresponds with C. So we write them in the same order so that all parts correspond appropriately. So in example 1, we are told that figure ABCD, so we have a quadrilateral here, ABCD is congruent to FGHK. ABCD is congruent to FGHK. Solve for all variables, so it looks like we have an X and a Y that we need to solve for. So segment FG is right here. FG is congruent to AB. Again, in the same order, FG is congruent to AB. So 3x minus 6 is equal to 9. We know if two segments are congruent that their lengths are equal. So we can set those two lengths equal to each other and we can solve for x. We have solved for one of the variables. Angle K is the one down here at the bottom left. And remember, this does not necessarily correspond with the bottom left here. Notice this one's been rotated. We would have to rotate it back in order to see where it goes. Or probably the best way to do it is to notice that, okay, K is last when we're listing out our congruence statement up here. So angle K is congruent to angle D. So 4x plus 2y is equal to 44. We know x is 5, so we can put that in here. Subtract 20 and divide by 2. X is 5, y is 12. The third angles theorem. The third angles theorem says if two angles of one triangle are congruent to two angles of another triangle, then the third angles must also be congruent. Two angles of one triangle are congruent to two angles of another triangle, then the third angles are also congruent. Which hopefully logically makes sense. We know that the sum of the interior angles of both are the same. So if this one's the same and this one's the same, and the sum of all of them is the same, hopefully logically it makes sense that the other one needs to be the same as well. And we could prove it algebraically as well. So I know that this and this are the same. Let's call that A. And if that's A, we know this one here is A. And we're told that a second angle is the same on both. Let's call that B. And because those are congruent, this one over here is B as well. And we're trying to show that this third angle has to be the same on both. But let's assume that they might not be the same. This one's going to be X and this one's going to be Y. Well, we know if we add up the angles here, A plus B plus X, these angles add up to 180 degrees. And we also know these angles, because they are the interior of a triangle, those also add up to 180 degrees. A plus B plus Y is 180. Hopefully we can still see, okay, those have to be the same. To take it further though, if both equations are equal to 180, we can use substitution. We could substitute this in, well, that in for the 180 over here. So it says A plus B plus X is equal to A plus B plus Y. Subtract A from both sides, subtract B from both sides. We get X has to equal Y, which again, I think logically makes sense here. Notice that we don't have to have congruent triangles for that to happen. I drew these so that they were congruent, but they don't necessarily have to be. If this is A and this is B, then this one down here has to be the same as this one down here. Example two says Elijah took a piece of fabric, which is this figure STUV. Looks like we've got a rectangle here. All right angles are defined. These parallel sides are congruent. ST and VU are congruent. It says that he cut it on the diagonal. It doesn't tell us which diagonal, but Elijah cut it right here to make some scarves for himself and Cam. We are asked to prove that those two pieces are exactly the same shape and the same size. To prove that those things are congruent, we need to prove or show that all of the parts are the same. All of the parts are congruent. So we know that ST is congruent to VU, right? So that side and that side match up. We also know that SV, segment SV, is congruent to segment TU. That's given. So I've got those pair of sides are the same. These pair of sides are the same. We also know that VT and VT, that matches up with itself, right? It's on both triangles. VT is congruent to VT. What property is that? That's the reflexive property of congruence, right? When something is congruent to itself. Hopefully that makes sense. We also know that angle S and angle U are congruent. And then because we have a rectangle here, we know these lines are parallel to one another. So let's look at angle SVT, this angle right here. Well, that's going to be congruent to this angle right here. Angle SVT is congruent to angle UTV, because those are alternate interior angles. And we can say the same thing about STV. STV is congruent to UVT. Because again, those are alternate interior angles. So we showed that we have 3 sets of congruent sides. We have 3 sets of congruent angles. Therefore, triangle STV, we went along the long edge and then along the hypotenuse, is congruent to angle UVT. I think I said angle, triangle, UVT. We can state that because congruent parts lead to congruent figures. And I know we didn't set up like the whole 2-column proof, but we kind of talked through each piece of it. We have 6 congruent things. We have congruent sides on all, congruent angles on all. If all the sides and all the angles are congruent, then the figures are congruent. Example 3. Example 3, we're given a figure here. And we are asked to find the measure of angle YXW. YXW. We want this angle right, a big one right here. We should be able to fill in all of the angles on this. But I guess the only one we really need is YXW. Let's take a look at this triangle right here. We know that this angle, 40, plus this angle right here, and it says that this angle and this angle are congruent. So if this one's 35, that one needs to be 35 as well. Plus, we're looking at the interior of this triangle, 40 plus 35 plus this angle right here. Put 3 things there because that's what we're looking for, and it's different than these two. Whatever that is, let's call that X. All those need to add up to 180. 40 plus 35 plus X. That forms a triangle. Really, that's all we need. 75 plus X is 180. Looks like X is 105 now. Why I wrote 110. So that full angle in here is 105. We could go through and fill out the rest of this. If this is 35, we know that this is 70 to add up to the 105. 70, 40, that's 110. And this triangle here needs to be 180. So this is 70 as well. 35, 35, that's 70. This needs to be 110. Notice there forms a straight line. That's got to be 70. It's a vertical angle. Also, it's a linear pair. 70, 40. That's 110. So this one needs to be 70 up here as well. Finally, one last thing, some properties here. This is nothing new. That's the only thing that's new is we've talked about these three properties many times. We talked about these three properties as they relate to equality. We've talked about these three properties as they relate to congruent segments. And we've talked about these three properties as they relate to congruent angles. Now we're going to talk about these three properties as they relate to congruent triangles, but they have the same name. The only thing that's different is we had the blank property of equality or the blank property of congruent segments. Now we have the blank property of congruent triangles. So it says for any triangle ABC is congruent to itself. We said that segment AB is congruent to segment AB. Anything is congruent to itself, even triangles. What is that? We actually used it earlier. That's the reflexive property of congruent triangles. We can also switch around the order here. We said before that segment AB is congruent to segment BA. For triangles, it says if triangle ABC is congruent to triangle DEF, then triangle DEF is congruent to triangle ABC. That's the symmetric property of congruent triangles. And then we know if these two are congruent, ABC is congruent to DEF. And then these two are congruent, DEF is congruent to JKL. Well, we can skip the middleman, right? ABC is congruent to DEF, and DEF is also congruent to JKL. It makes sense that all three of them are congruent, so we could state that ABC is congruent to JKL, and that is our transitive property of congruent triangles. That's it for the notes in 4.2. Reach out if you're having questions.